Hello and welcome to this module. In this module, we will focus on gamma ray detection. We'll go over what a gamma ray is and what are the different ways that the gamma ray is going to interact with some material. We're going to call it gamma matter interaction. And then we'll go to the different types of gamma ray detectors there are. And this will then conclude the first module out of the several series that we will have. A gamma ray, or a photon, I should say, more generally, is an energy particle, and it's basically a quantum of light. It is just like a packet, and you'll learn more about it in your modern physics class or your whatever class is proceeding after this. And the quanta of energy, meaning there is it's only very small packet of energy, is characterized by the wavelength or the frequency of the gamma ray. This is the energy of the photon, or of the quanta, and it is basically Planck's constant times the frequency. Nu here is the frequency. Another way you can rearrange it is Planck's constant times c, which is the speed of light, over lambda, which is the wavelength. Lambda, the wavelength, is described from the peak to peak. It turns out that the photon has both a particle and a wave duality. We're going to focus on the wave part of the particle, the wave nature of the particle, and you can see this from the double slit experiment in the lower right. Let me turn on the highlighter from the lower right corner. So this is the lower right corner. Here there is a photon source emitted, so this is the wave fronts, and when it goes through two slits, these two slits are very, very small. When it goes through these two slits, at the other side, you can see that there are this pattern. This is an interference pattern, and it indicates the wave-like nature of the detector. If there are particles, you basically see two streams coming out of that. But this experiment, which was done almost over 200 years ago, shows the wave nature of the detector. Wave nature of the gamma ray or the photon. In this graphic, you can see that there is different characteristics or different names for the different wavelengths of the photon. Over here with the largest wavelength is a radio. These are huge, very long wavelengths and very low frequency. These have very little energy. You can see here that when the wavelength is very large, this value is very small. Again, this frequency is very small, the energy is very small. But let's increase it to all the way up to gamma rays. You can see that the frequency here is very high. This is the number of times it oscillates for some unit time. Or the wavelength here is very small. And this is basically what a gamma ray is. And we will focus only on this particle. The way the gamma rays interact with matter is via several different effects. These are the major effects that we will discuss today, starting with photoelectric effect. Photoelectric effect usually is the dominating effect in lower energies, and this is shown by this graphic right here. In this graph, there is the energy in the x-axis, and this is in units of MeV. MeV is a unit, or MeV is million electron volts or mega electron volts. It's basically a unit of energy. It's the amount of energy you need to kick up an electron 1 volt of potential. So this is an x-axis is energy. On the y-axis is atomic number, or Z. It basically says how large the atom is. So you can see that for larger Z, the effects are slightly different, but let's just break this down into different rectangles and squares. When we go to higher energies, in this median energy right here, the main dominant interaction is via Compton scattering right here, and we're going to talk about it as well. Finally, at very high energies, the dominant form is pair production. Pair production occurs if the gamma ray is larger than 1.2 MeV. Photoelectric effect, which was discovered a little over 100 years ago at the turn of the century, the 1900th century. The 1900, and it was later mathematically described by Albert Einstein, and that's what he won the Nobel Prize for. He describes how the photon gets absorbed and an electron gets emitted. This is the photoelectric effect described in this picture. When a photon gets absorbed, this electron gets its energy and then ejects. We call this a photoelectron, but it ejects with an energy minus the binding energy. So this is the energy of the photoelectron. H nu is the energy of the original photon coming in. Minus EB is the binding energy. You will learn this more in 311 and 312 next year. The next gamma matter interaction is Compton scattering. And Compton scattering, just like any scattering you learn from your physics 1 class, a gamma ray comes in with some energy and it scatters. And because there is a conservation of energy and conservation of momentum, an electron gets recoiled. And the energy that gets recoiled is proportional to the angle of the scattering. So this is theta. So theta is in relation to the original vector of the gamma ray. So gamma ray comes in, scatters at some angle theta, and an electron gets ejected. In the 311, in NERS 311, you'll calculate how to estimate the energy of this electron, but this is given with this equation. This is the Compton scattering equation. This effect was actually discovered by Arthur Compton, who got the Nobel Prize for this. What this describes is the energy of the scattered gamma ray. So this is energy of the scattered gamma ray, and equates it to this following formula. This is the energy of the incoming gamma ray right here, and it's over 1 plus the energy of the incoming gamma ray over MEC squared. Naturally, you learn from everything E equals to MC squared. This basically describes the energy of the rest electron. ME is the mass of the electron, C is the speed of light. So this is the energy of the rest electron. And then you multiply that by the quantity of 1 minus cosine theta. Again, theta here is the scattering angle. Another way to view this equation is also by the wavelength shift. So lambda here, remember from 2 slides ago, is the wavelength of the gamma ray, right, peak to peak. So the wavelength of the scattered gamma ray minus the original wavelength is this quantity right here. And H, I remind you again, is Planck's constant. It's just some quantity that you will learn more about next year. The final gamma matter interaction is what's known as pair production. It basically, when some kind of energy gets deposited, you create the particle and the antiparticle. So this is summarized by this cartoon. This gamma ray comes in, and then an electron and positron gets produced. And these subatomic particles each have an energy half of the original incoming gamma ray. So the electron has half, so let's say if this is 1 MeV, if this has 2 MeV, this electron has 1 MeV of energy and the other one has 1 MeV of energy. This was first seen in what's called the cloud chamber. You will learn this again in Michael Hua's presentation following my presentation. This is the gamma ray coming in, and then a pair production occurs. Now, the reason there's a curling over here is because they apply in this cloud chamber a magnetic field or electric field. And you can see by how much it curves, you can estimate the mass and also the energy. That's why if you look at CERN, that's basically how they estimate all these exotic particles and their masses and how much energy they have, is by they see the curving. If something has more mass, the curving will be much slower. In this case, the positron electron has more mass. I'm not quite sure why this, it could be the angle at which you're looking at. That's why the curling looks different. But they should be curling at the same amount because they have the same mass. But this is one way to see, this is a visual representation of the actual pair production effect. So this is the 3 summary: photoelectric effect on top, and in the middle is the Compton scattering, right? I'll show you the recoil electron. And at the bottom here is a pair production. Now, one thing I did not talk about the pair production is that when that one particle is an electron, the other one is a positron. The positron is the antiparticle of the electron. When it slows down, it deposits energy, it creates it ionizes everything around it, basically creates like electron hole pairs around. It slows down, and when it slows down, it will annihilate with an electron that is inside the material that it's traversing. When it annihilates, it creates a annihilation photon. So this is a 2 511 gamma rays coming out of the end of the track. These can interact or escape. So this is the three main interactions. And we will look at the gamma ray spectra, or the energy spectra associated with these effects. This is what we call an energy spectrum. This is also like a histogram, if you remember from your high school statistics. Energy is on the x-axis, and this is basically the number of counts per bin. This right here is the Compton continuum. The reason there is a Compton continuum is because there is different angles in which I should use this one. There are different angles in which the gamma ray curve scatters. If it scatters at angle 0, it deposits no energy. But if it backscatters, it comes in and backscatters, it deposits something called the Compton edge. If the gamma ray scatters multiple times, or if there's a photoelectric effect that occurs, then a photopeak is a resultant of all the energy deposited from that interaction. So the photon is fully absorbed by the detector. Pair production slightly complicates things. This is a pair production event, and here you can see the 511 escaping. So each of them is 511. So that's 2 times 511 is about 1.2. So whatever the photopeak is, the double escape peak, which means the escape of each of the 511s, is the energy of the original photon minus 2 times 511. 511, I'm going to remind you, is the rest mass of the electron. So minus 2 times 511. The main idea behind gamma ray detectors is to convert the gamma rays into some signal that we can measure. So this is going to be represented by this box. The gamma ray comes in, interacts with this box, and converts it to a signal. Next, you have some electronics that records this signal and makes an energy spectrum of it, or however processing you want to do. We will focus on these different types of photons to the photon to signal converter. These are the main popular photon to signal converters. On the left one is a scintillator. It gives you good resolution, and the way it does that is that if a gamma ray comes in, interacts with the detector via any of the gamma matter interactions we've discussed before, the electron being recoiled or being produced will lose its energy and will luminesce. Basically, it will create a lot of optical photons, and you can see this in this image right there. These optical photons bounce around until they hit the photocathode. The photocathode converts the photon light into an electron via the photoelectric effect. The electron gets lensed into these diodes and gets multiplied. This module right here is called the photomultiplier tube. It basically amplifies your signal and creates a larger signal from that very small signal of light coming in. You want to amplify it because you want to make sure that the electronics can record it. So this becomes a very large signal. I'm drawing the signal with my hands. So these are the different types of scintillators. You can cut them into different geometries. This is a cube, this is a cylinder, and there are bars as well. There are a lot of popular ones. The other one is a gas or ionization chamber. There is a gas inside, and when the gamma ray comes in and deposits some energy, an electron gets recoiled, but also a hole is present. That hole travels also to a respective electrode, and we'll talk about it some more in the next module. And as it's moving to the electrodes, you are creating some signal which you can record by your electronics. And one form of it is a Geiger counter. You've heard this maybe in movies or in your other classes. And this Geiger counter is basically a counter. It counts the number of quanta deposited in the gas tube. The last one is a semiconductor-based detector. Just like all the other ones, the gamma ray comes in and creates an electron hole pair. The electrons and the holes drift to the respective electrode, and then it gets recorded by some electronics or whatever processing form you have. And this is the main detector that is done in our research group. right here, this is a semiconductor. It's made out of cadmium, zinc, and telluride. You may have heard of semiconductors made out of silicon or thallium bromide, but this is the main detector that's being used by the University of Michigan Orion Group. There are different applications of gamma ray detectors. One of them is for astrophysics. There are others. There are a lot of astrophysical objects that emit gamma rays, including supernova, black holes, the sun, and getting a gamma ray spectra gives you a lot of knowledge on what these processes are actually happening. You can know what type of elements are on, you can know the process or the temperature at which something is burning. But what I present here is the gamma ray spectrum on the moon. So here there's an orbiter made by this research group, and an orbiter that orbits the moon and collects the gamma ray spectra coming from the surface of the moon. And they look at these two different elements, thorium and potassium. And they take the ratios of the gamma rays coming out, the number of gamma rays that are coming out of the surface, and they can somehow relate a model that this has a similar ratio to that of Earth. So their leading theory right now is that a big asteroid came and hit Earth and split it into two, or broke a piece of it, and over time it clumped together and formed the moon. And then I can also talk about how much time it took, but this is different models that is used by the community. Another one is via Homeland Security, which is a lot of usages for gamma ray detectors. One of them is the portable isotope neutron spectroscopy. Neutron spectroscopy is a little misleading because they use neutrons to do gamma ray spectroscopy. So here they have a neutron generator, which emits neutrons onto some detector material. To some target. In this case, it's an artillery shell. This target, when the neutrons interact with the target, they get captured, or some kind of some kind of gamma ray gets emitted. When this gamma ray gets emitted, it's detected by the gamma ray detector. And using what gamma rays come out, you can use these different signatures to try and estimate what the actual target is. So in high explosives, you can see that the most used elements in the explosive is hydrogen, carbon, nitrogen, oxygen. And they take the ratios of them and try to infer what kind of explosive it is inside. There's also chemical warfare agents that they use the different elements to try and estimate what is in there. And with that, we conclude the first module of the series.